Okay, so we're going to take a look at the graphs of the secant and the cosecant. So let's start with the secant. Now, again, what you see here is the graph of the cosine, and I'm going to graph over that, not the graph of the secant, or this isn't the graph of the secant, but I do want to use the fact that the secant of x, right, the reciprocal identity, is 1 over the cosine of x. Okay, so right away, a couple things that we should take note of is the reciprocal of 1 is 1, so the values of 1, those are going to be both on the secant and the cosine graph. And the same for negative 1. So these points here, all right, those are all going to be part of both the cosine and the secant. Right, now when we take the reciprocal, one thing or one kind of operation I want you to keep in mind is that 1 over a small number equals a large number. Okay, and also the fact that 1 over 0 is undefined. Okay, so that means that at these points here, the secant is just going to break, right? It's undefined. I cannot divide by 0. So right away we start seeing the major difference between the secant and our cosine function is this idea that, well, the domain is not going to be all real numbers, right? Wherever the cosine crosses the x-axis, that's going to be a an asymptote, or a place where the graph of the secant is undefined, right? And we see that this happens, the space between them, right? More importantly, right? So when we do define the domain and the range, is that the space between these asymptotes is pi units, right? To get from pi over 2 to 3 pi over 2, we add a factor of pi. And the same thing from pi to negative pi over 2, we subtract pi, right? But they're each spaced pi units, all right? So that's where this 1 over 0 is undefined. Now the reciprocal, notice what happens, well, as the numbers get less than 1, these numbers get bigger and bigger, right? So here, just so you get an idea of what I mean, 1 over a small number, let's say 1 over, let's say 0.1, something less than 1. We see it's 10. All right, now let's make that number smaller. Let's add a bunch of zeros. All right, so you see the reciprocal of that 1 over a very small number is a very large number. All right, so what happens here is as this approaches 0, the values of x, or excuse me, the value of the denominator, 1 over cosine x, the values of the function, they're getting smaller and smaller. So what's happened to the secant? It's doing this. It's getting larger and larger. All right, undefined at pi over 2, right? Because we cannot divide by 0. But the closer we get to this, right? Closer and closer we get to it, the larger and larger that becomes. All right, where it just kind of almost looks like it's pi over 2, but it just approaches. All right, and the same thing happens here, right? As we get closer to this asymptote, it does something like that. All right, and the same thing here. Right? We're just on the negative side, right? 1 over a very small negative number is a very large negative number. So it shares the point -1, but beyond that, as this goes closer to pi over 2 on this side, it does something like that. Okay, and here, and for drawing asymptotes, so the graph of the secant looks something like this. Right, notice similar to the cosine, it is also as well periodic, right? The period is 2, right? If we go from 0 to 2 pi, excuse me, 2 pi, not 2. All right, we get one complete graph of the function. Okay, so some properties of our secant function. All right, now when you graph it, You don't always need to graph the cosine along with it. I like it as kind of a rule, or just kind of a guideline as to what it looks like, right? Whenever I try to imagine what does the secant function look like, I always think of the cosine, right? Because I just don't remember that right off the top of my head. But the two that always stick in my mind is the secant, excuse me, the cosine and the sine, right? Those I just have implanted in my memory essentially. But and from those I can regenerate the secant of x and the cosine of x. But now let's take a look at the properties of secant of x. Excuse me. Okay, now the domain is going to be, well, we can see what it is, right? It looks like it's all real numbers except, right, there are exceptions because it's undefined here, right, at pi over 2, and any addition of pi units from pi over 2, or subtraction if we're going in the other direction. Now, a way to represent this, we're going to look at some fancy math notation, right, using set notation here. So just kind of follow along with me here. So the domain, right, we're going to use set notation, right, set builder notation, is any value of x as long as x does not equal to pi over 2 plus any addition of pi, right, times k, right, where again, k is not just any real number, k is an integer, right? So 1, 2, 3, 0, -1, -2, -3, etc. Right? And now we could see if I had 1 pi from pi over 2, that gets me to 3 pi over 2. If I had a negative pi, that gets me to negative pi over 2. Right? And if I had, let's say, a negative 2 pi, that'll give me to negative 3 pi over 2, etc. Right? Another way to represent this is you can write this as a union of intervals, right? So this is set notation. The interval notation is this notation here, where we have 2k plus 1 over pi over 2 and 2k plus 3. All right, now the reason it's kind of it's more involved, the set notation, is because we do have to omit these values of pi over 2, 3 pi over 2, etc. Right, so it's a union of those essentially across the real number line from negative infinity to positive infinity, except, hence the open parentheses, at these values here, right? And all these values are consecutive even integers, excuse me, consecutive odd integers divided by 2, right? So when k is 0, we get pi over 2 and 3 pi over 2, and that's this interval here. All right, let's say when k is -1, we get negative pi over 2, and this is pi over 2. So we get these values here. Okay, so it's just a way to represent them using the interval notation. It just gets complicated because of all the asymptotes. Okay, now let's take a look at the range. Right, now as we can see from the graph, right, the range, now we're looking at this part of the graph, right, not the cosine function, right? This is not part of our graph, right? So as you can see from the range, it goes from 1, including 1, all the way up to infinity. And then there's this gap between 1 and -1. But after that, the range goes from -1 down to negative infinity. Right? So we can represent this using, again, our set builder notation. That would look like this. So the range are values of y, such that the absolute value of y is greater than or equal to 1. Okay, so that'll include the negative values as well, right, that are bigger than 1, right, with that absolute value. Now, in terms of, so this is set builder notation. In terms of interval notation, it's a lot less complicated than this, right? The two intervals would be from negative infinity to -1, inclusive of -1, right? From here to here, we have a gap, and then union from 1 to infinity. Okay. All right. So it looks like that for the range. Another property of the secant is that it is continuous and smooth on its domain. All right, important distinction, that last part, right? Smooth on its domain. Okay, so within the negative pi over 2, within pi over 2 and 3 pi over 2, it is continuous and smooth. So there's no corners or cusp or any kind of odd behavior. All right, so it is even. Let's designate these as kind of bullet points. Is an even function. And has a period of 2 pi. Much like its reciprocal function 1 over cosine x. All right, so those are the properties of the secant, right? The parent function, the most basic function, without changing anything of it, right? So the parent function has these properties. All right, so let's take a look at, we saw how we did the secant. Let's take a look at the cosecant. Okay. Now we're going to use the same kind of ideas that we did before in the secant graph to graph the cosecant, right? So cosecant is 1 over the sine of x, right? And similar as before, we see using the reciprocal, these points where it reaches its maximum and its minimum, right? They're going to have in common between the cosecant x and the sine of x. All right. And same as before, wherever it crosses the x-axis, we're going to have asymptotes. So the y-axis is an asymptote, pi is an asymptote, 2 pi, right? Negative pi is an asymptote. All right. And let's do this one as well, negative 2 pi. All right. And notice here that while they don't occur at the same positions as the secant of x, they are spaced out equally, right? Between the asymptotes, we have pi units. It's easier to see here since they start at 0. 0 to pi units, pi to 2 pi, another pi units. Okay? And then the same thing when they share this point, when the sign gets smaller and smaller, we get that same reciprocal effect, right? Where it kind of breaks the graph, right? As this gets closer to 0, approaching 0, the reciprocal function gets larger and larger and larger. All right, same thing in this direction. As we approach this value of 0 here, it's larger, larger, and larger. All right? And then the same thing in the negative direction, right? As we approach 0, but here on the right side of pi, the value gets larger and larger in the negative direction. All right? See here. Right, and we see that we have a period of 2 pi. After that, it just starts kind of repeating itself. Here. Okay, so now we have the graph of our cosecant function. Now, very similar, again, to the secant. Again, it just kind of has that shift. All right, it's not at the same position as the previous one. All right, so let's take a look at some properties of the cosecant. Of the function g of x equals to the cosecant of x. All right. Okay, so for the domain, we use the set builder notation. So we have x such that x is not any multiple of pi, right? So pi, 2 pi, 0, negative pi, negative 2 pi. The next one would be negative 3 pi, or 3 pi on the right side. So as long as x is not some multiple of pi, right, where again we have to make the distinction k is some integer. All right. And in terms of interval notation, we get this large U here, where we write it like this, k pi, and then k plus 1 pi, right? And all this is stating is these are consecutive integers, right? K is an integer, k plus 1, that would be the next integer, okay? So don't let this kind of fancy notation intimidate you, right? We can, just as long as we realize what this is doing, it's a union of an infinite amount of intervals, and these intervals that we're representing here are the ones that are consecutive integer multiples of pi. All right. The range is a bit easier to represent, similar to the secant. The range is y such that the absolute value of y is greater than or equal to 1. Right? And in terms of interval notation, negative infinity to negative 1, right? Inclusive of negative 1, union of 1 to infinity. All right. Okay, see, this union is the same as this larger union, except this one is doing a wide number of intervals, and this is just doing these two intervals, putting them together. All right, so that's the domain, that's the range. The function is also continuous and smooth on its domain, okay? Okay, if it's not in domain, but it's not continuous there at the functions where it's undefined, the function is odd and has a period of 2 pi. Okay, all right. So now we've gone over the graphs, the parent graphs of the cosecant and the secant and their properties.